In this video, we're going to learn about light, sound, and making changes to waves. Specifically, we're going to also learn about the Doppler effect. Let's start by learning about some basic facts about light. We need to know these facts before we move on, because as we move on in the waves unit, we're going to need to use some examples to learn some of the phenomena that's going to happen. And so we're going to use light and sound often. And so we need to know some basics about light before we get going. Okay, we all know that, or we've discussed in the past, that the medium that light always travels through is the electric and magnetic field, because it is not a mechanical wave, but it's an EM wave. Brightness is determined by the amplitude of the wave. The amplitude is related to the energy. Remember that energy is proportional to the amplitude of a wave squared. Therefore, the more energy a wave has, or the more amplitude, the brighter it appears, because it basically overloads the senses in your eyes. So whenever we say that the light is really bright, we're saying the amplitude is high. Color is determined by frequency. Some people think that the color is determined by wavelength. This is often taught in chemistry. However, it actually is directly related to the frequency, and sometimes the wavelength just changes as a byproduct. The speed of light is commonly thought of as 3 × 10⁸ meters per second. It is a common variable that's used in all kinds of different places in physics, and it's really important to know this fact. The symbol that we use is the letter C, and this is a common constant, and so it is constant throughout the universe so long as that light is in a vacuum. And it's like pi, where pi is a given or known number that's always 3.14. The speed of light in a vacuum will always be 3 × 10⁸ meters per second. You can change the speed theoretically by changing what medium it's in. The problem is the medium is always the electric and magnetic field, so you're not really ever changing the medium, and so the speed of light never really technically changes. However, when you shine light in air or shine light in water, it's actually slower in air than it is in a vacuum, and it's even slower in water than it is in air. Now, why is that if the actual field is the electric and magnetic field and not the water or the air itself? Well, the reason is because the presence of additional particles like air particles or water molecules, what that does is that kind of mucks with the electric and magnetic fields. This is a very loose way of going about it, but hopefully it shows how it can slow down the light on average, or give you a sense of how it slows down the light on average, but it doesn't slow it down as a whole. So for example, between the actual individual molecules, so if we have water and there's a water molecule here and a water molecule here, in between these molecules is some space, and the light actually still goes at this speed in between that space where there's nothing, but the presence of those molecules do slow it down on average. All right, another thing that you should be aware of is you should be aware of all the different kinds of electric and magnetic waves. Visible light is only one type. All these facts are really true about all these electromagnetic waves. You need to be aware of the different types of waves that are considered electromagnetic and their order. So when I say their order, I mean from longest wavelength to shortest, or you can also think of these as lower frequencies, and over here are higher frequencies. So the lowest frequency but longest wavelength is radio, and it goes microwave, infrared, visible, ultraviolet, X-ray, and then finally gamma rays have the highest frequency and shortest wavelength. Some facts about sound similar to that of light. The medium for sound waves is typically air, because that's what it's traveling through when we're usually doing problems. Loudness, just like brightness, is determined by the amplitude. You may have heard of people talking about using an amp or amplifier in order to make their sound of their speaker system louder. That refers directly to this term, amplitude. The pitch of a sound is determined by frequency. For those music lovers out there, if you know an instrument and you are tuning your instrument, sometimes you'll have to get something in order to help you, and they'll often talk about the exact frequency of that pitch. For example, one of the frequencies for C is going to be 256 hertz. The speed of sound is going to be 343 meters per second. Now, this, unlike light, is relative to aspects of the medium, because the medium is a physical medium, air. And so it depends on what's going on with that air. If you're at room temperature, and if you're at sea level, then the speed will be around 343 meters per second. Honestly, you don't need this for the AP test, because you should either calculate the speed of sound in the problem, or you should be given the speed of sound in the problem. But you might need this if you're doing practice problems from the textbook or from WebAssign. All right, the last way to change the speed is by changing the medium as with any other wave. So if you send the wave into air that is, or from air into water, then the wave will either speed up or slow down. It actually speeds up in water. And if you just change something about the air itself, if you heat it up or change its density by going to a higher altitude and thinning out that air, it'll also change the speed by a little bit. Now that we have facts about light and sound, we need to review a couple of facts that we should already know by now. These facts are important as we move on to the content that we need today, and they're things that you should already know or should sound very familiar. One of these first facts is the equation for the speed of a wave, v equals lambda f, or as they often write it on the AP test, lambda equals speed of the wave divided by the frequency of that wave. Now, even though this is the equation for calculating the speed of the wave, these variables, lambda and f, do not determine the speed of the wave. The speed of the wave is strictly determined solely by the medium. The only way to change the speed of a wave is by changing the medium itself. No amount of changing of lambda or f directly changes the speed, only the medium. Waves are also created by oscillating the medium. That's an important fact that we need to be aware of, and we'll talk about today as well. And the last is that when we deal with a wavefront diagram, if you recall, a wavefront diagram is a diagram that shows waves from a two-dimensional plane. So, for example, if this is something that's tapping, maybe this is water and someone's tapping the water over and over and over again in the same spot, it would make ripples in the water as ringlets. And this is a representation of those waves. And the distance between these lines will always represent the wavelength, as we often draw the line representing the crests. So the distance between crests is that wavelength. What we would like to do now is look at 4 different ways in which we can change the speed of a wave. Whenever we do, we are always going to use the same equation. On the AP test, they only give you one equation, v equals lambda f. Now this one equation, when you do a problem, will be used oftentimes more than once. So what you'll do is you'll use v equals lambda f with the information they give you and solve for something that you need to know and set a baseline for something. And then usually something in the middle of the problem changes, which changes something about the equation, and then you have to use the equation again with a new number. This is a very common process that you're going to use over and over again with most of the problems that you'll see on the AP Physics test. So whatever changes, whenever something changes, there's always the same 3 things that happen. Whenever something changes, one of these 3 variables, speed, wavelength, or frequency, will directly change as a result of whatever happened in the story problem. Another thing that will happen is one of these 3 variables will not change at all and will not be affected by whatever event occurred. And the last thing is, if one of these variables change and one of them stays the same, the other one has to change as an indirect result. So 2 variables will change. One will change directly as a cause of the story, of whatever's happening in the story problem, and one will change indirectly, while the other one stays constant. The first and very common example of a change that occurs in a problem is when the medium changes. If the medium changes, the thing that changes directly is the speed of the wave, because remember, the medium directly affects the speed of the wave. So the speed will either increase or decrease. The thing that will not be affected is the frequency. This is hard for us to remember, and you've got to think of some way to remember it. What works best for me is I think of shining light into water or something like that. If I have a red laser and shine it into water, the red laser does not turn blue just because it went into a new medium and slowed down. It stays the same color. And we know that for light, the frequency determines the color of the wave. It's the same thing with sound. If you ever put your ear against a door and listen into a conversation, it's not like the pitch of whatever you're listening to increases or decreases. If you're listening to your mom and dad talk, they don't now sound like chipmunks at a high pitch or sound really with a really low pitch. They may sound muffled because not all the energy gets to your ear, but the pitch is still the same. So the frequency is not changed by going into a new medium. If the speed goes up, for example, and the frequency stays the same, then the wavelength has to go up. Similarly, if it goes down, if the speed goes down, the wavelength has to go down. This is an example where light is shined from air into water, and that will slow the light down. As a result, the wavelength gets shorter and squunches together. This is very similar to cars on a freeway. When the cars are flowing fast, there's a lot of space between the cars, but as traffic kicks in and it starts going a little bit slower, that space between them gets smaller and smaller. It's the same thing with waves. These bumps start squishing closer and closer together. Another way in which we can make a change with wave is by changing the source itself. Now, remember, how do we make a wave? That's by oscillating the medium. So if you are tapping water, for example, and you're taking your finger and you're going tap, 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 right in the center or in a certain spot, it would make rings and waves, and it would go out in all directions from the center of your tap. Now, it might look like this or might look like this, right? So what it looks like depends on how frequently you tap it. If you tap it extra frequently, like tap, 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 it's going to have more waves jammed in the area, and it's going to look like this. If you tap it slower, tap, 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 it's going to look more like this. So what is the thing that's actually directly being affected? Many of us want to say the wavelength because we see that wavelength is smaller. That's not true. Remember, in the story, it specifically says we're changing the source's frequency. We're changing the frequency of oscillation, the frequency at which we tap. Therefore, the thing we directly change is the frequency of the wave, because whatever the frequency we tap the medium with is the frequency that the wave will have itself. The thing that will not be affected is the speed of the wave, because regardless of how I tap, it's still the same medium, thus it has to have the same speed. What is affected indirectly is the wavelength. So because I'm tapping it more frequently, the waves bunch up together and they're closer together, and therefore the wavelength is smaller. So the speed might stay the same, but if the frequency goes up, the wavelength has to go down. All right, another example would be to move the source of the wave. So instead of tap, 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 tap all in one spot and the rings going out in all directions, if I tap and move my finger while I tap, the pattern would look more like this. Now, when I do this, we can see that the waves bunch up in the front because I'm moving my finger forward each time I tap towards the wave that I just made. So in front, the waves actually shrink, or the wavelength gets smaller. But behind, the wavelength actually gets longer and they spread out more. So what's being directly affected is the wavelength itself. What's not being affected? Well, it is still the same medium, so it must be the same speed. And what is indirectly affected is the frequency. But notice how I'm writing it. I'm not just saying frequency, I'm saying the frequency we observe. So the frequency that this person over here sees, feels, hears, or whatever kind of wave this is. Now the reason why I'm being careful to say the frequency that's observed is you'll notice if this is water waves that are being created by tapping the surface, the tap, 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 tap frequency, or the frequency of the source, is still the same whether you move your finger or not. But because the waves might bunch up, the frequency that he sees becomes different. This is hard to explain with this example, so we're going to look at some other examples to explain it further. This phenomena has a name though, and it's called the Doppler effect. So you should be aware that the Doppler effect is basically a phenomena where the observed frequency changes due to the relative motion of either the source of the wave or the object observing the wave. Okay? And it all has to do with the motion of either of these two, and it's only the observed frequency. The source can stay the same as what it used to be, but the frequency the observer sees, hears, or feels will be different. Here's a classic way to look at it. If you think of something like a fully automatic paintball gun that's shooting someone over here, right? Here's a sensor, and this paintball gun is firing every single time the light flashes. Over here, it receives the paintball every single time the light flashes. The rate at which we send fire, 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 fire is the same at which the guy receives it over here. He gets hit, 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 hit. However, if whoever's shooting wants this person to be pummeled by these paintballs more quickly, they could be firing still at the same rate, fire, 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 but if they're running towards the person at the same time, these paintballs will all get squished up together because you're moving closer to where the last paintball was fired before you fire the next one. And so that space becomes smaller. And then even though the frequency at which you're firing is still the same, the frequency at which they receive it becomes greater, and it becomes a faster pace at which it receives those paintballs. This is true with waves as well. If you're standing up here, you're going to get those waves more frequently than you would if you were standing in the back, because those waves are bunched. In a nutshell, this is how we look at it. When the source is moving towards a listener, the speed of the wave still stays the same, but the wavelength in front bunches up. So the wavelength becomes smaller, the speed stays the same because it's the same medium. This makes it so that the frequency has to go up. But again, this is the observed frequency is higher, not the frequency of the source, but the frequency this person feels, hears, or sees. So what would that mean? If this was a light wave, if someone had red light that they're shining at the person while moving towards the person, that red light will have a different color because the frequency is different. So even though it's still a red flashlight, the person observes something a little bit more maybe orange or closer to yellow, okay, depending on how fast that object is traveling. Now granted, don't try this at home because the actual speed required to get this to happen is astronomically high. However, it's more noticeable with sound because those speeds are not that high that is required to get this phenomena to be observed. So often we talk about Doppler effect, and we'll continue to do so in terms of sound. So if something was emitting a sound, a certain pitch, something like that, as they travel towards someone, what the person hears will actually be a higher frequency. So even though the pitch emitted is they'll hear a higher pitch because of this squishing of the wavelength and the increasing of the frequency. Similarly, if we wanted the person in this paintball war or whatever to suffer longer, we could run away from the person while firing, and even though we fire at the same rate, the space between each paintball will increase, and the rate at which they receive the paintballs will go down. So similar to last time, in this example, we have the source running away from the observer, and so the waves that are coming towards the person are spread out. So the wavelength goes up, but because it's the same medium, the speed stays the same. This means that the frequency observed goes down. Now, you have all probably experienced this in your life. This is a very common example. I mean, the last time you committed a crime and you were running from the cops, because, you know, that's so common, right? You are running around and you're hiding from the cops, and the cops might be driving by and their sirens are blaring. Now, as the cop drives by, though, when the cop is traveling towards you, the waves are squishing, and so the actual pitch you hear isn't the pitch it emits, but is actually a little bit higher pitch. And then when the cop moves away from you, it'll be a lower pitch. So the actual frequency you hear is, or that it sends, the original frequency will be whatever this is. But what you hear while it's traveling towards you is a little bit higher pitch. So you really hear woo, woo, woo. And as soon as that cop car passes you, it lowers in pitch because then you're receiving the waves that are spread out. So it sounds like woo, 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 and it gets lower in pitch. Now, because this is such a classic example, a lot of people, they talk about the Doppler effect as if it has to do with the fact that the siren gets louder as it gets closer to the person and quieter as it gets farther. Well, that's true. That has nothing to do with the Doppler effect. Sure, the siren gets louder because it's getting closer to you, but the Doppler effect is the fact that the pitch itself is higher when moving towards you. And it doesn't matter how close it is. As long as it's moving towards you, it's the same higher pitch. And as soon as it passes you, it's the same lower pitch. That's the Doppler effect. There are two ways, however, to get the Doppler effect to occur. We've discussed how to make the Doppler effect happen with the source itself, the source of the wave move. The other way is to have the actual observer be the one that moves. So if we have a stationary source, so let's stick with sound because it's nice. So a stationary or parked police car that's giving off a siren, turning on their siren. And instead of the car moving, if you start running towards the car, you will still have a change in the observed frequency, but the reason for it is different. The waves are still equally spaced, and whether you're moving or not, you still see the same, if you could see the wave, you still see the same space between those compression parts of the wave. So the wavelength actually still stays the same. The thing that changes is the apparent speed of the wave. Now, it's still the same medium, so it still goes the same speed, but to your perspective, it looks like the wave is faster. Think of if you're driving on the freeway and you're driving at 20 miles, sorry, hopefully you're not going 20 miles an hour on the freeway, and you're going 60 miles an hour, and someone behind you is going 61 miles per hour. Now, to your perspective, it doesn't look like you're going 60 miles per hour. It looks like you're standing still. And it doesn't look like they're going 61 miles per hour. It looks like they're moving forward very slowly at 1 mile per hour. It's the difference or relative speed that matters. So according to the observer, it looks like as he runs into the waves, that the waves are coming at him extra fast. They're not. They're still going the same speed relative to an observer who's standing still, but it appears it's moving faster. Again, the wavelength stays the same because it's still the same space. So if the speed changes and the wavelength stays the same, the frequency will then change as a result. So if the speed goes up, the frequency also goes up. We can do the same thing with paintballs. All right, so if we have this time the paintball source staying stationary and sending its waves, or its paintballs, but the observer running into it, he's going to receive it at a faster rate because he's closing the space between the two. And it looks like those balls or those paintballs are traveling extra fast. So to summarize, as the observer moves towards the source, the waves appear to be going faster. The wavelength is still the same, so therefore the frequency also increases. This is, again, the observed frequency. Similarly, we can be running away from the source, and if we do that, the frequency that we receive should seem to go lower. All right, so in this case, to summarize, right, we're saying we're running away, and so it looks like the speed of the wave is going slower than it used to be. And so now, because the wavelength stays the same, the frequency will also appear to be lower. So we still have the same change in observed frequency, but it's for a different reason than when the source itself was moving. One last thing that we want to look at, and that is what happens when the source moves faster than the wave it's actually making. This is a picture of the waves created by a stationary source. So imagine someone tapping the water, tap, 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 tap here, but the location of where they tap always stays the same. If we start to move forward slowly, it'll start to look like this, like we've seen, where the waves start bunching up. However, if the source itself went just the exact same speed as the wave, that means it creates a wave, and then by the time it creates another wave and taps again, it's still on the same wave front that the last wave front that it just created. And so if it's going the same speed as the wave itself, it'll look like this. Now you'll notice these are getting more spread out, and these not only are getting more bunched up, but right in front, they're all right on top of each other. So if these were water waves, that would be a crest on top of a crest, on top of a crest, on top of a crest, right? And so when we have a crest superimposed upon another crest, we would get an extra big wave because of constructive interference. And so what happens is there's a very large wave built up here. Now, if you start going extra fast, faster than the wave itself, the same kind of thing happens. But by the time you make the next wave, you're in front of the last wave. And so there still are a lot of these lines that intersect, but they all make this V shape. Now, what that means, if this was a water wave, is that there would be an extra big wave right here, right, in this shape of a V. I'm sure you've probably seen something like this before. If you've ever been on a speedboat, this is very common. This V right here is called the wake, and it's an extra big wave created by the superposition of a bunch of wave crests right on top of each other. This also happens with the speed of sound. If you go faster than the speed of sound, there'll be, instead of crests being upon crests, it'll be compressions upon compressions, which will make the amplitude of the sound really large and really loud. And this is called a sonic boom. Okay, so when something goes faster than the speed of sound, it actually gets greater and greater. Here is a picture of with the water wave, right? And so this is going really fast compared to the speed of the wave, and there's the wake, the V behind it. Here's a picture of an airplane going faster than the speed of sound, and you can see again that V behind it. And the reason why you can actually see it is because this is compression, right? Because it's a longitudinal wave, and so what's happening is it's actually squeezing the water vapor in the air into a cloud, and so you can actually see it behind you. But when that large amount of compression hits your ear as the airplane goes by, that's what makes that loud boom sound as it passes by.